Okay, this hour we'll talk about some other mechanism of TCP. The first one we'd like to talk about is TCP flow control. As we mentioned before, TCP has two communication peers, sender and receiver, right? But actually, the sender does not know the capability of the receiver, so we don't know what is the memory size used by the receiver. We don't know the CPU power. We don't know the network connection capacity of the receiver. So basically, the sender will not know how fast or how slow the sender can send this TCP segment out to the receiver. So basically, only receiver knows how what is the current state, okay, situation of the receiver. So TCP flow control is a mechanism that the receiver can notify that how fast or how slow the server can, sorry, the sender can send. Okay, so take a look at this figure that right here. The flow control means the receiver controls server, so server won't overflow receiver's buffer by transmitting too much too fast. Okay, and as we mentioned before, there is a 16-bit header in the TCP header. Okay, so we use this specific field called receive window or receiving window to tell the server you should send faster or you should send slower. Okay, so take a look at this figure. Okay, that is the receiver. Okay, that is a receiver. Okay, when sender and the receiver open a TCP connection, they have to exchange some information, right? It's exchange some information. At that moment, receiver should tell, or we use the word advertise. Okay, what is the free buffer space right here? Okay, we take a look at the right hand side. The yellow part is the buffer called receiving buffer. Okay, that is the total memory allocated by the receiver to receive the segment data. Okay, the segment data right here. Okay, and typically right here, depending on different operating system, typically the default value is 4096 bytes. Okay, so the receiving buffer is limited. Okay, so when sender and receiver transmit receive those TCP segments, okay, those segments will be put into this buffer, right? So at here, there is a value called R window, called receiving window. The receiving window is the free buffer space of the receiver buffer. Okay, you make sure you make sure you understand that. Okay, the entire buffer size is receiving buffer, and the free space is called receiving window. Okay, so the receiver should explicitly report, or we say advertise, the free buffer space in the receiving window field and the TCP header every time when the receiver send an ACK back to the sender. Okay, the receiver should write down how many free buffer space in bytes, of course, okay, can be used by the receiver, and put this number in the TCP header in that receive window field. Okay, so that the server the sender will receive the free buffer space, so that the sender can keep monitoring how many bytes are there in the free buffer space. So basically it may looks like this. At the very first beginning, okay, the receiver side has lots of free buffer to use, okay? At when sender sends send segment, okay, to a receiver, so the receiving window size goes down, right? But at some moment, okay, those buffer data will be sent to the application process layer 7, right? So at some moment, okay, the receiving window goes back to a larger number and go down, go larger, go down, go larger. So basically, the sender can keep monitoring the receiving window to understand what is the current free buffer space used by the receiver. So if it keeps in a very low level, then the sender should send the segment more slower, so that the free buffer space will not be overwhelmed by overflowed by the sender's segment. Okay, so that we say that sender limits the amount of the on egg, which or we call in-flight data, to receiving window. So it can guarantee the receiver buffer will not be overflowed, will not be overwhelmed by the sender. So that is an advertisement mechanism, okay, controlled by the receiver. So the receiver can report how many free buffer space are there, and the sender will monitor the free buffer space so that we will not overflow receiver. Okay, so that is called flow control. As we mentioned before, UDP has no flow control. TCP has flow control. So you can safely send messages from your sender to a receiver by using TCP, because TCP will control the sending speed by the sender. Of course, it is advertised by the receiver. Okay. So next one is what we call TCP management, or say handshake. It's right here, handshake. Before exchanging data, sender receiver will do handshake. So before sending messages, both of them need to agree they intend to establish such kind of connection, and then they agree on certain connection parameters. As I mentioned before, sequence number, and of course they have to exchange the current receiving window number at this moment. Okay, so let's simply take a look at this one. Okay, there are several different ways to exchange parameters before you indeed exchanging messages. Okay, in textbook, okay, we introduced two different kind of handshake. The first one is called two-way handshake, but two-way handshake has some flaws. So basically, we don't use two-way handshake in TCP. It's right here. Basically, we use TCP three-way handshake, but here we will introduce why two-way handshake is not good enough to establish a connection. Okay. So for example, there's a sender and there is a receiver. Okay, so the sender will choose some parameters, for example X, and send a connection request to the receiver, and the receiver will agree such kind of connection and send the parameter back to the sender. Okay, and you can see that only two packets exchange between server and receiver, and think of that you are the receiver. Okay, so you wait there and you receive a connection request. So you know server would like to communicate with you, and you send an agreement back to the sender, so that you currently at a establishment state, because you know as intend to do such kind of connection, and you send some acknowledgement back to the sender. So you are ready to receive and send packet, right? But think about the server right here. When you choose a parameter and send a request, okay? But what if the agreement, the acknowledgement of the agreement get lost? And you will never get such kind of agreement, right? So you will never go to establishment state. So at this moment, receiver are ready to send and receive message, but the sender does not know what is the current state because it's waiting for the agreement, right? So on the right hand side, because we have variable delays, so server does not know it should keep waiting or it should reset the connection or it should terminate the connection because it has to wait. Okay, and sometimes, okay, retransmitted messages, for example, if the server, if the sender send a timer right here, and it eventually times out because it does not receive, for example, right here, okay, timer, okay, because it does not receive the agreement from the receiver, right? Eventually send timer, it will send duplicated request message, but at this moment, the receiver would feel very strange, right? Because I already agree the connection previously, but why did you send a retransmitted message to me and using the same parameters? So it is quite strange right here, right? Because the server and client are cannot see the other side, so the communication state would be a little bit strange. Okay, so that is the reason why we don't use two-way handshake. That means we don't simply use two packet to set up the connection. So here we have some strange scenario right here. They are simply just some examples, some random example right here. Okay, at the left-hand side, we agree to use parameter x to communicate with each other. So at this moment, we can send data and egg. That is okay. Okay, that is okay. But in the middle, if let's see, there is a timer, right? If there is a retransmit request, okay, and that is a very, very late request, okay, the client, the receiver at the right hand side, basically it already agree your connection, but we don't know why the sender just simply don't send any data. Maybe the network is very congested, so it does not receive the corresponding acknowledgement or the next packet does not arrive. So at this moment, server does not know the receiver already in established state. So at some moment right here, the receiver does not get any data, right? But it is already at established state. But at some moment, the server, which means the R, okay, at the right hand side, the server forget X. That is because the receiver terminate the connection. Okay, if there is a late request, which is this one, and the receiver or the server will establish again But at this moment, maybe the server, the sender already terminate all the communications. That means any retransmitted request or late request or delayed request will cause the receiver to establish a connection again. But that is not what the server intend to do. Okay? So at this moment, the receiver open the connection, but the server does not. The sender does not. Because at this moment, both of them terminate the connection, but there's a late retransmitted request arrive at the receiver after the sender and the receiver terminate the connection. So the receiver open the connection, but the sender does not intend to do so. So we call it half open connection. Okay, half open. When you open a new connection, as a receiver, okay, you need to set up a socket number. You have to set up a buffer. Okay, you have to consume some resources. Okay, so if you have a lot of a half open connection, it is not good for the receiver. Okay, it is just one of the example that late request or retransmit request will cause half open connection. Okay, and again right here, okay, it is very similar. Okay, at this moment, okay, the server and the sender and the receiver already close the connection. Okay, if there is a late or retransmitted request and there is a late data packet sent to the receiver will reopen the socket again and receive the data again. But actually those are simply just retransmitted request, retransmitted data. They are not actually data. Because server thought it will be a retransmission, so the receiver, when receiver receives such kind of retransmission, it will discard the retransmitted data. But if there's some late retransmission which is arrived at the receiver after they close the connection, the receiver will receive all those data without confirmation. Right? That is the reason why two-way handshake is not that good, because they only use two packets to open the socket. At the third example, the receiver does not need to check if the sender intend to open the connection again. Okay, so that is just one of the several example which two-way handshake scenario is not good. So but basically you can just skip the two-way handshake because it is not the right thing to do. So basically we use three-way handshake. Okay, so here is A, B. Okay, we have a A to B, and the other one is B to A. Okay, we take a look at the green part. Okay, for the very first time, when A would like to send the packet to B, and it will set the same bit to 1. Okay, make sure you know that it's right here. The same bit is right here. Okay, when you want to open a new connection to the receiver, you have to set this specific bit to 1, and you randomly choose a sequence number, for example X. So at the right hand side, when B receives such kind of connection request, and it knows, okay, I would like to egg your connection request. That means, okay, I accept your connection request, and I know that your sequence number S starts from X. So I expect your next packet should be start from X plus 1. Okay? So that is from A to B. And the other part is that when A sends such kind of a request to B, and at this moment, B will also send a SYN packet to A and set up another sequence number. This sequence number is used from B to A. Okay, sent from B to A. And after A receives such kind of request, and it will act the request and say, okay, I know the sequence number you choose is Y. So the next sequence number I expect is Y plus 1. So basically, we have 4 different message exchange. Okay, the first one is called SYN. Okay, and here is egg, the green one. Okay, and the other is again is the SYN, and the other one is the blue egg. Okay, basically 4 message has been exchanged. So A understand that B accept the connection, and B agree the parameter X chosen by A. On the other hand, B send a SYN packet to A with sequence number Y chosen by B, and A agrees such kind of Y parameter, so he send the X back to the B. So basically, they mutually agree the parameters used by the other side. Okay, so in this case, the reason why we use three-way handshaking is that the blue SYN packet sent from B and the green egg sent by B, they're both from B to A, right? So basically, they usually they those 2 segments will be sent only in one single segment. So only 3 segments will be exchanged, but the second segment has the green egg and the blue SYN. Okay, but basically there are only 1 packet will be sent from B to A. So verbally, okay, we will talk. We use the word TCP three-way handshaking. Three-way means there are 3 packets, okay, and it reads as SYN egg, 3 packets. Okay, and here we have the state right here. That means the state of B and A, they are a little bit different. Okay, think about one. Let's take a look at the right hand side. Okay, originally B listens at certain socket. Okay, when A would like to communicate with B, okay, when B receives the first SYN, then B goes to SYN received state. Okay, and at that moment, the green egg and the blue SYN will be sent out, right? And after B received the last green egg, then it goes to the next state called establishment. Okay, that is at the right hand side. So at the left hand side for A, initially it is at listen state, and after it sends the first SYN, green SYN, to B, and it goes to SYN sent, and it will wait the first blue SYN comes from B, and the green egg comes from B, and it enters the establishment state, and then send the last egg back to B. So right here, This figure is the TCP finite state machine I get from the TCP RFC, but we will not go over the entire state. But you can simply just take some time to take a look at this part. Okay. So at the right hand side we have okay, we take a look at the left hand side first. Okay, from A to B. Okay, so first initial state is the listen state. Okay, at the listen state, the client or the sender, okay, will send its first green SYN to a receiver, right? So after that, it goes to SYN send state, and the sender will wait at SYN send state. Okay, and on the other hand, okay, at the right hand side, the server will wait at listen state, and it will receive a SYN and goes to SYN received state. And at this moment, it will send the first SYN packet and as well as the ACK packet back to the sender, to A, right? So the SYN ACK will be sent. So again, we go back to here. After the sender, the left hand side A receive the send ACK, it will send the last ACK and goes to establishment state, right? So again, the ACK will receive right here to make the finite state machine transit to the establishment state. So basically, the state we write the state we write here is exactly the same as we described in page 75. Okay, but the actual finite state machine is a little bit complex, so we'll not go over all those finite state machine. But you can see that the actual finite state machine of TCP is right here. Okay, there are lots of states and lots of events. Okay, so that's it. Okay, and the last one is when the client and server or the sender and the receiver like to terminate the connection. Okay, so the first one again is that the server will send a TCP segment with fin bit set, and let's assume the sequence number is x+1. Okay, so when the receiver receives such kind of termination request, it will ACK the termination, and the next expected number should be x+1. Okay, so that's is the termination. Okay, requested by client or OS. Okay, so if when right hand side the server or the receiver, okay, they can still send data right here, because the green segments, they only specify S will not send any packet to right hand R, but R has its own sequence number, has its own acknowledgement, right? So R can still send data from right hand side to the left hand side until a right hand side server would like to terminate the communication, and then it will send a packet with SYN bit set, and let's assume the current sequence number is Y. After that, S will act such a kind of termination, and the next sequence number will be Y+1. So at this moment, sender cannot send data, receiver cannot send the data as well. Okay, so both of them agree to terminate all those would like to terminate the entire TCP connection. Okay, that's it. And as we know that that is a fin packet, right? That is an egg, green egg, and that is the green fin packet, and that is the egg packet. Okay, and again, although there are 4 different packets, they have different meanings, but usually, but usually these 2 segments will be actually 1 segment because they are from R to S. Okay, because most of the time when S terminate the communication, the R has no data to send. Usually. So again, usually we call this it is also a 3-way termination, and we call it fin egg and egg to terminate the communication. Okay, the state right here. Okay, you don't have to remember all the things because they are too complex, and the textbook does not mention too much about the states. Okay, you simply just know we have 3-way handshaking. Use SYN bit to exchange parameters, and we have 3-way termination. We use FIN bit to close the TCP connection. Okay, that's it. But there's one thing very important is right here. Okay, as we mentioned before, because it is a two-peer communication, they are remote peers, right? So when the client send the last egg, which is the last blue egg, to the server, okay, we have no idea if the egg arrives at the receiver, at the server or not, right? Because it is the last egg, that's the segment exchange between S and R. So we don't know if this arrives or not. Because even after the server receives such kind of egg, it will not send any data back to the sender, right? So here we have a very strange mechanism, is that when client send the last egg out, it has to wait 2 maxima segment lifetime. It cannot directly close the socket. It has to wait. Because what if this egg does not arrive at R? If, I say if, okay, if this packet get lost, okay, there should be a timer right here, and the timer will time out somewhere right here, and it will send the fin. Of course, it is a retransmit fin again. So in case the last egg might get lost, so the server, so the client has to wait just in case the server did not get the egg and the timer time out, and it will retransmit the fin again, just in case. So that is at the server side, because it is the last one who sent the last egg, so it has to wait. Okay, so that is TCP closing a connection. Okay, so the next topic is a little bit different. It's called congestion control. Okay, congestion control means don't mix it up with flow control. Flow control, we said it is a mechanism handled by the receiver, right? So receiver will advertise the receiving window to the server, to the sender. So the sender will not overwhelm the receiver. But the congestion control right here is that all the routers, all the internet routers, they may suffer from they may suffer from long delay, right? So the router, okay, ideally the router should explicitly tells the sender to slow down its sending rate so that the router, the buffer, will not be full, right? But actually in the internet, we don't have such kind of mechanism for the routers to notify the sender. So the sender should come up some mechanism called congestion control to make sure the sender will not send packet too fast, so that the router might drop packet. Okay, so here we have several different scenarios to discuss the congestion control. So the first one is right here, scenario number 1. But however, right here I have to mention that this scenario is an ideal scenario. Actually, internet does not look like this. Okay, here is the assumption right here. Okay, we have a router. We have a router right here, and the assumption is a little bit strange. Okay, it has infinite shared buffer. That means we have unlimited buffer size. It is not realistic, right? Okay, so at this moment we have 4 hosts. Okay, A set up a TCP to C, B send a TCP connection to D. Okay, the transmission rate is right here, Mbps. Okay, so we have one router. Okay, not that realistic assumption, infinite buffer, and the input output link capacity is Mbps, and we have 2 flows, the red one and the blue one. Okay, and there will be no retransmission needed because the router has infinite buffer size, so no packet will be dropped, so there will be no retransmission. Okay, so take a look at this one. We have a that is 74321, right? 74321. Think about one thing. If the message comes from their 7, okay, its sending rate is lambda n. Okay, you have to notice that the rate is the sending rate at layer 7, not layer 4. Okay, so at the right hand side, when layer 4 send the message to its corresponding process at layer 7, the rate is called lambda out, and that is the throughput. Okay, we have talked about throughput previously, right? So if there is no packet loss, no retransmission, if everything is fine, we have infinite buffer, and there will be no packet loss, no retransmission. The sending rate lambda in right here should be equal to the lambda out throughput, right? Because no packet is lost, and it should be nearly half of the link capacity because we have 2 TCP connection. Okay, one is the red one, the other is the blue one, and we will talk about what is the reason why it is exactly half of the link capacity if we have 2 connections. Okay, that is the assumption. Very simple scenario 1 right here. Okay, we have finite buffer, infinite buffer, we have no loss, we have no retransmission, and the sending rate should be exactly as the same as the throughput. Lambda in equals to lambda out, and two connection, they should have each one should have half of the capacity. Okay, that is a definition of scenario number 1. So let's take a look at scenario number 2. Now we have finite buffers. Finite buffer indicates packet lost. Packet loss indicate retransmission. Right? Because we have finite buffer, so buffer might fill, and the router might need to drop the packet, so the sender might have to retransmit the packet. So currently, again, at layer 7, the sending rate is lambda n, but at layer 4, the sending rate right here, the definition, the notation is lambda prime n. It should be the original data plus retransmitted data. Let's take an example right here. For example, the sending rate at layer 7 is 100. Okay, it is a rate 100. Okay, so basically, originally the 100 should be right here, but the routers might drop the packet, so maybe 20 units of the original data dropped at the router. So right here, only 80 comes to the right hand side, and the lambda out is right here. Okay, because it is TCP, right? We discussed reliable data transfer, right? So additionally, 20 data will be retransmitted, because at the right hand side, when C receives all those 80 packets, it will know, depend on the sequence number and the acknowledgement number. C, the receiver knows, okay, 20 unit of packet get lost. So the sender, which is A, will eventually retransmit the 20 packet to the at the left hand side. Okay, but at this moment, those packets are retransmitted packet. They are handled by layer 4. So actually, layer 7 does not retransmit the packet, because the retransmission is done by layer 4. So at layer 4, include the original 100 data plus the 20 retransmit data. The entire lambda prime n is larger than the original lambda n at layer 7. So that is at layer 7, that is at layer 4. So at layer 4, more data has been sent to layer 3, more than the data sent from layer 7 to layer 4 because of retransmission. And this number is called offered load. So at the right hand side, at the right hand side, actually the additional 20 unit of data will be received because of the retransmission at the right hand side. Okay, so that is scenario number 2. Okay, but think about one thing. Okay, we have 2-1, 2-2. Okay, this is the first scenario of scenario 2. Okay, think about one thing. If we have limited buffer, so right here, limited buffer. Okay, so if we have limited buffer right here, again, because it is scenario 2, but there is a very strange assumption. Sender sends only when router buffers available. That means router's buffer is limited, but somehow, magically, host A knows the current state of the buffer. So A only send packet to the left-hand side to the router if there is a free buffer space. In this case, buffer will always free. The buffer always has free slot because the sender A magically has perfect knowledge of router's buffer. So sender only send packet when buffer is available. So no packet loss, no retransmission. At this moment, lambda m equals to lambda prime m equals to lambda out. So you can see that. Okay, but this kind of idealization is not exist in real world because host A never has some magic way to know when the buffer is available or the buffer is full. So 2-1 is only one of the idealization. Okay, it never happens. Okay, so think about one thing. 2-2. If the sender has some perfect knowledge, okay, the assumption is a little bit strange again. The packet can be lost, dropped at the router due to full buffers. But the sender knows magically, okay, when packet has been dropped it, and only resent if packet known to be lost. Okay, so again, that means packet might the router might drop the packet. Okay, so but A magically knows which packet should be retransmitted. So in this case, again, let's take a look at it. And it's in this case again, lambda prime n should be larger than lambda m. Because the TCP need to retransmit the packet, you magically know it is lost in the router. So the lambda m prime is now larger than lambda m in these cases. Okay, but at right here, lambda out is right here. Okay, there's 7. At the receiver side, the lambda out is the rate, is the throughput rate, right, received by the layer 7. Although there are some packet lost, so the even if A send use half of the R capacity to transmit original data plus retransmit data, but at the right hand side, the lambda out is never goes to half of R. Right? Because at the left hand side, okay, we can at the left hand side, the host A should spend some link capacity to retransmit the data that dropped right here. So lambda prime m now it equals to half of the R. But actually at the layer 7, the lambda out should be equals to lambda n, which is a little bit less than half of r. So right here, the throughput never achieves to half of r because it needs to waste some capacity due to retransmission, and the retransmission data will waste the link capacity. And we the value we care about is the lambda out, which is the throughput at the receiver side at layer 7. So it should be a little bit less than R/2. Okay, that is because lambda prime n is larger than lambda n because of retransmission. Okay, take some time to comprehend these things. Okay, the other part, that is the realistic scenario 2-3, unneeded duplications. In this case, again, we have finite buffer, so packet may drop right here. And again, packet can be lost, dropped it at router due to full buffers requiring retransmission. Okay, requiring retransmission. Okay, but again, timer. Okay, but the sender's timer can time out and send 2 copies, both of which are delivered. Okay, again, the original data is 100 unit. Okay, so 100 unit, and because packet might drop at the router, right? So plus retransmission is 20 right here. But you know, timers might time out too early. So when timer time out, but actually maybe that packet, the timeout packet, has already arrived at C, right? Maybe the packet indeed arrived at C, but the ACK is delayed, so the ACK does not go back to A, so timer timeout. So at this moment, certain amount of packet will be retransmitted due to timer timeout, but maybe that retransmitted timer timeout packet has already arrived at C, but you waste some link capacity to transmit such kind of timeout retransmitted data. So basically, it will be something like this. The 20 is caused by drop. The certain amount of retransmission is caused by timer timeout. So actually, again, lambda prime n is again larger than lambda n, and it is even larger than the previous scenario 2-2. So right here we can see that there are still some throughput is wasted due to unneeded retransmission. Because the unneeded retransmission is caused by timer, maybe actually the packet has arrived at C and its corresponding ACK is delayed, so A will eventually receive such acknowledgement, but the timer timeout, so A sent the packet out before it received the late acknowledgement. So it again wastes some link capacity to do such kind of timer timeout retransmission. So the lambda out right here never goes to R/2. Okay, so there are 2 different reasons. The first one is the dropped packet. A need to retransmit the packet at layer 4. But actually at layer 7, only 1 copy of the retransmission will be received by C's application, right? And the second reason is that the timer might time out because of the delayed packet. delay ACK packet. So it need to spend some link capacity to retransmit the timer timeout retransmission. But this retransmission will only one copy of the retransmission will be copied to the layer 7. So basically, at layer 4, there are some other packet has been sent. Okay. It is exactly the same thing. Okay, which I mentioned before. That is a more complex example, but we simply just take a look at this one. Okay, if we have 4 connections at the end, the lambda out will be R/4. But we will talk about why 4 connection will share the capacity next hour. Okay, we will talk about the reason why the situation they will divide the entire bandwidth fairly. Okay, we will talk about this later. Okay, so this is the last slide. Okay, we simply just draw all the figures right here, the textbook. Okay, we will stop right here. So in the next hour we will finish the TCP